Okay, good morning. Uh, Today I want to see the session 2, that is the first topics of unit 1. Okay, so we'll see one by one. This is the first unit. The first one having three different titles. First one, the origin of biopotential and its propagation. Second one, type of electrodes, and third one is recording problems. Okay, so the origin of biopotential and the type of electrodes are very important topics. So most of the questions are asked from these two topics. Okay, recording problem is new topic added when compared to previous syllabus. Okay, right. Then today we're going to see the origin of biopotential. So the origin of biopotential, this is a session 2. Okay, the objective of today's session is the after this session student can understand the biopotential, what is biopotential, then what is action potential, what is resting potential. Okay, so we will see one by one. Okay, right. But the definition, bioelectric signal, what is bioelectric signal? Okay, so before studying the bioelectric signal, what is electrical signal? So electrical signal is it is a energy, that is a flow of electrons in a copper wires or metal body. Okay, right. So it is represented by voltage and current. Okay, right. So the electrical signals are generated from generator. Okay, right. Bioelectric signals, that is also electric signal that is generated by electrochemical actions. Okay, right. So can you say any electrochemical power generation methods? Do you know? So one of the basic method, you I think you were studied in your school. That is the basic method, the generating the electricity from lemon. Okay, do you know that? So generating electricity from lemon. How do you generate? By using a two electrode, copper and aluminum electrode. Okay, we insert into the lemon. Okay, so from the lemon, the electric, that means electrons are flowing through the electrodes, so you can glow any one LED. Okay, right, around 1.5 volt to 2 volt, I think so. So this is one of the electrochemical generation. Electrochemical, that is a electrochemical electricity generation. Then another one thing is the battery. For example, in our car or bike we are having battery. The battery also producing electricity based on a chemical reaction. Okay, inside it has some acids, some electrodes. Okay, right. So bioelectric signals are the electric biosignals are usually taken to be electric current produced by sum of electric potential difference across a specialized tissue, organ or cell system like nerve system. Thus, among the best known bioelectrical signals. So we are measuring the bioelectrical signal in our hospital. Okay, right. So the electroencephalogram, that is a EEG, that is used to measure the brain waves. Then magnetoencephalogram, MEG, then other one GSR, then ECG, then EMG, HRB. These are the some bioelectrical signal that is measured from the human body. Okay, right. Then the origin of biosignal, where it starts. Biopotential are produced as a result of electrochemical activity of excitable cells. Electrochemical activity, that is an important point, that is electrochemical activity. Bioelectrical signals are produced as a result of electrochemical activity of excitable cells. That is, in our body is a combination of cells. The cells having some chemical content. Okay, these chemical content generate potential. Okay, so bioelectric signals are ionic voltage due to electrochemical activity. Ionic voltage. Okay, what is ion? Ion is a positive or negative charged element. Okay, atoms, that is called ion. Okay, that is moving around the cells. Okay, so it generates some electricity, that is a biopotential. So the transducer are used to convert the ionic potential into electrical voltage. Ionic potential means the charge. Okay, the charged molecules or charged particles. Okay, So that is around, it is placed around the cells, okay, inside the cells and outside the cells, okay. So by using the electrode or the transducer cell, there are same almost, okay, that will use it to convert the ionic potential into electrical voltage, okay. So from this, the origin of biopotential is cell, okay. Cell generate the potential, okay. How it is generate, we will see. Before seeing the biopotential generation, first of all you have to know about some points related to cell. What is cell? The cell is a basic unit of everyone, the human, animals, plants, etc., living things, okay. The consider human body, around we are having 100 trillion cells, okay. All cells have ability to reproduce the new cells, okay. It's a nature. Then each cell has nucleus, okay, that is important thing. This part of the cell, so the part of the cell is, first one is nucleus, that is in center of the cell. Then around the nucleus we are having the cytoplasm, that is a liquid, okay, that is a cytoplasm. Then the cytoplasm is covered by cell membranes, okay. Nucleus is covered by nucleus membrane, okay, right. Then the group of cell liquid chemical active chemical things, that means that is called protoplasm. The protoplasm contain the water molecules, sodium ions, potassium ion, then chloride ion, okay. So the sodium and potassium, that is a positive charged ion, chloride is a negative charged ion, okay, right. Then the type of biopotential, okay. So now let's study the cell, okay. Cell having the three important elements, sodium, potassium and chloride, okay. So sodium and potassium are positive, chloride is a negative, okay. So these are the ions, these ions are used to generate biopotential, okay, right. Then the biopotential divided into two types. First one resting potential and the second one is action potential. Okay, resting potential and action potential. Okay, what is resting potential? So before we are going to see the resting potential, what is ion? The ion is a charged atom in a body fluid. Ion is a charged atom in a body fluid. Okay, so the ions are potassium, sodium and chloride. Okay, so the cell pyramid enter potassium and chloride ions inside the cell. So the cell has cell membrane. Cell membrane allow to enter potassium and chloride ion, but block sodium ion. Okay. So from this, the sodium ion outside the cells, then potassium and chloride ion inside the cells. Okay. So sodium ion is positive, potassium ion is also positive, chloride is negative. So potassium and chloride is present inside the cell, okay. Sodium ion present outside the cells. We are measuring the resting potential between inside the cell and outside the cell by using electrode, okay, right. What happens, see this diagram. The circle indicates the cell, okay. Inside the cell we are having the two things, that is a potassium ion and a chloride ion, okay. Then one electrode is connected with the voltmeter positive terminal from the center of the cell, okay. And another one is outer the cell we are having sodium ion, n plus ion, okay, right. So the n plus ion is connected with the, that is the outer of the cell is connected with the another one electrode, that is a reference electrode, that is mostly connected with the ground, okay. So main electrode is connected with the inside the cell, reference electrode connected with the outside the cell. So now the voltage is negative. Why the voltage is negative? Because the sodium ion is positive, okay. The ground terminal is connected with the positive terminal, and the plus, and that means the positive terminal of the electrode is connected with the positive terminal of the electrode voltmeter is connected with the electrode that is present inside the cell, okay. So now we can see the negative charge also present inside the cell, okay. So inside the cell we are having the negative charge, outside the cell we are having the positive charge. So the potential is negative potential, that the voltage is negative voltage. So minus 60 millivolt to minus 100 millivolt, okay, that is a resting potential. So this is a default condition. What is the meaning of resting? Rest, that means there is no movement of cell, sorry, so no movement of charged particle. So charged particle present outside the cell, that is sodium, that is positive. Inside the cell, that is potassium and chloride. So mostly it's a chloride is mostly present, so it is a negative voltage. So this is a resting potential. Resting potential range is minus 60 millivolt to 100 millivolt. Okay, right? So this is a resting potential. Now how this resting potential moved into action potential, we will see. Okay, so before that we have to see one equation, that's a Nernst equation. Okay, since the electric and the diffusion force actors are opposite each other, so the equilibrium state is achieved. At the steady state, the potential using Nernst equation is given by. So equilibrium means inside the cells, inside the cell, the charge inside the cell and the charge outside the cell both are equal. Okay, that is both are in same strength, then only the equilibrium state is achieved. The at equilibrium state we are having the that is we are using one equation, that is a Nernst equation, that is the equilibrium potential for potassium measured in volt. That is for potassium, but potassium, where it is potassium inside the cell. Okay, at equilibrium condition, the charged particle potassium K plus, that is equal to RT divided by ZF, then logarithm of K. Okay, logarithm of K star divided by K minus plus divided by K divided by K plus die. Okay, see, K, actually this is the description is given below the equation. R is the universal gas content. Okay, equal to 8.314 joule. T is the absolute temperature measured in Kelvin. Z is the number of eliminated charge of the ion. Okay, then F is the farad, that is a capacitance unit. Constant equal to 96,485 coulombs. Then K plus O is the extracellular concentration of potassium measured in mole into meter minus cube. Okay, right? Then K plus I is the intracellular concentration of potassium. Okay, so this is a Nernst equation. This is a important 2 mark question. Okay, many times this question is asked in university examination. Define this equation or write the next equation like that. Okay, right? So this is another one diagram. So this diagram shows the resting potential. See the left hand side. Okay, right? So here that is potassium present inside the cells. Outside the cell we are having the sodium ion. Okay, so at one condition, at some condition, the sodium ion cannot enter into cell. Okay, that condition is a resting potential. Okay, right? That is a negative voltage, that is in polarized condition. A resting potential is a polarized condition. Okay, right? Then after that, action potential. How action potential is takes place. Okay, consider if you are sitting in your table. Okay, so in your consider your class, you are sitting in your table. Okay, you are just sleeping. Okay, suddenly anyone hit your head, what will happen? You are immediately getting angry and you wake up. So that is the action. So same concept is applied here. The resting potential is negative voltage initially. Any external stimulation is applied to the cell, what will happen? The cell is immediately active. Then it is allow the sodium ion inside. Okay, the cell membranes resistance is decreased. It is used to allow the sodium ions. So on the transfer of ions between the between the cell, that not between the cell, so inside the cell to outside the cell or outside the cell to inside the cell, it will happen some potential. This moving of charge creates some electric potential that is called action potential. Okay, right. So these things is called depolarization. When the charge particles are in rest condition, that is called polarization. After that, the external stimulation is applied to the charge particle, applied to the cell, then the charge particles are start moving between the inside the cell and outside the cell. That is called depolarization. Okay, so during the time of depolarization, we are getting action potential. Okay, right. Then the membrane potential is also called as resting potential. This is due to different concentration of ion. Okay, so the membrane potential is also called as resting potential. Okay, right. So already I told these the points. Okay, due to the different concentration of ion, the membrane potential is generated. Okay, cell in resting stage, that is in polarized condition, resting potential is minus 60 millivolt to 100 millivolt. Okay, right. That is the next one is the action potential. So action potential, when will action potential happen? Action potential happen when some stimulation applied to the cell. If any stimulation is applied to the cell, the cell body, that is allowed to enter sodium ion inside. Okay, sodium ion inside. Okay, at the time the potential present, that potential is called as action potential. Okay, action potential is due to stimulation, external stimulation. Okay, this is the action potential diagram. So when the external cell is excited by external energy, so sodium ion enter into cell, it increases the ionic current flow. So cell charge particles moving, when the charge particle is moving, that creates the current. Okay, right. So see the here some moving of charge particle inside the cell, and some potassium particles moving outside the cell. Okay, so this process generates some electric energy that is called action potential. Okay, so this moving happen, after that it is generate action potential. After some time, the sodium ion entry is stopped. Okay, so this process is not continuously executed, so it is executed some particular time. So after some time the sodium ion is stopped, then current flow is reduced, then cell membranes resistance is increases, and it is reversed back to original state. Okay, this process develops resting potential. Again the cell enter into resting potential. Okay, so always the cell is enter into present in a resting potential. Whenever we are applying the external energy or stimulation to the cell, it will moving, it will allow to move some charged particle inside to outside or outside to inside. That time it will generate the action potential. Okay, right. This is a graph. So this graph indicates the resting potential and action potential. Okay, right. So the resting potential is below zero, that is in negative voltage. Okay, whenever we are applying the stimulation, see at time millisecond, at 1 millisecond we are applied some stimulation. Okay, then after applying the stimulation, it is rising phase. Okay, so this cell allow the particles moving inside or moving outside, whether it is a rising phase, then it is reaches to peak value. Okay, plus past 40 value. Then after that, during the peak time, large amount of charged particles moving between moving inside the cell or outside the cell. Okay, right, or vice versa. So then after that, the sodium ions movement is stopped. Then cell membrane resistance is increases. Then that is called falling phase. Okay, right, falling phase. Then falling phase reaches to negative voltage. Again it is entered into resting potential. Okay, right. So this is a graph used in our resting potential, sorry, action and resting potential. Okay, right. This is a important graph that is also asked in 2 mark question. Then another one important question is sodium pump. What is pump? What is water pump? Water pump, that is used to get the water from bore or well. Okay, right. Same way, sodium pump means it is take the sodium ion outside. The water pump take the water outside from ground. Same way, sodium pump, that is used to take out the sodium ion from the cell. Okay, so from the cell the sodium ions are taken outside. That process is called sodium pump process. The process is to transport the ion quickly to outside of the cell. Okay, right. Now the cell is polarized again. This process is called repolarization. So initially the cell is having potassium and chloride inside, sodium outside. That is the initial condition, that is a resting condition. At the time generate resting potential. After that we are applying some stimulation. At the time the cell is vibrated, then it is allowed to enter sodium ion inside the cell. So sodium ions are filling inside, then potassium ions are moving outside, where this process generate action potential. Okay, that is called depolarization. Okay, then after that the sodium ion entering the cell is stopped. Okay, then the resistance is increases. Okay, right. At the time the action potential decreases to very low and it is entered into resting potential. After that sodium pump process is applied. So large amount of sodium ions are present inside the cell, that is moved outside. Okay, immediately very fastly it is moving outside. This process is called repolarization. Okay, the rate of pumping is proportional to sodium concentration, sodium ion concentration. Okay, so this is a sodium pump process. Then another one important law is all or nothing law. This is also important. Two more question. Okay, the method by which the cell is excited, then the action potential is always same for any given cell. That is a all in nothing law. The method by which cell is excited, then the action potential is always same for all the cells. Okay, any given cell. So action potential is same for any given cell, that is based on method of exciting the cell. Okay, these are all or nothing law. Okay, then net height of action potential. Net height or maximum amplitude of action potential, it is defined as the difference between the potential of depolarized membrane at the peak of action and resting potential. Actually BAK, that is peak, BAK. Okay, so peak of action and resting potential, it is defined as difference between the potential of depolarized membrane at the peak of action and resting potential. Okay, so that is a net height of action potential. Another one is the absolute refractory period. It is the time duration in which the cannot respond to any new stimulus. The cell cannot respond to any new stimulation. Actually, absolute refractory period, at the time the cell cannot respond to any stimulation, external stimulation. So it is generally is 1 millisecond time. Then relative refractory period means it is one during which another action potential can be triggered, but higher stimulus is required to reinitiate action potential. Actually, currently the cell is in action potential. At that time, we need to generate another one action potential. We have to give some external stimulation. That stimulation is very high. Okay, right. So it is another method, that is a relative refractory period. Other time it needs more stimulation to enter into action potential. Okay, so it is happened for several milliseconds. Okay, right. So this is a resting and action potential. So we will see some on a small video of animation how this process takes place. Okay.
or membrane voltage, refers to the difference of electric charges across a cell membrane. Most cells have a negative transmembrane potential. Because membrane potential is defined relative to the exterior of the cell, the negative sign means the cell has more negative charges on the inside. There are two basic rules governing the movement of ions. They move from higher to lower concentration, just like any other molecules. Being charge-bearing particles, ions also move away from like charges and toward opposite charges. In the case of the cell membrane, there is a third factor that controls ion movement: the permeability of the membrane to different ions. Permeability is achieved by opening or closing passageways for specific ions, called ion channels. Permeability can change when the cell adopts a different physiological state. Consider this example. Two solutions of different concentrations of sodium chloride are separated by a membrane. If the membrane is equally permeable to both sodium and chloride, both ions will diffuse from higher to lower concentration, and the two solutions will eventually have the same concentration. Note that the electric charges remain the same on both sides and membrane potential is zero. Now let's assume that the membrane is permeable only to the positively charged sodium ions, letting them flow down the concentration gradient while blocking the negatively charged chloride ions from crossing to the other side. This would result in one solution becoming increasingly positive and the other increasingly negative. Since opposite charges attract and like charges repel, positive sodium ions are now under influence of two forces. Diffusion force drives them in one direction, while electrostatic force drives them in the opposite direction. The equilibrium is reached when these two forces completely counteract, at which point the net movement of sodium is zero. Note that there is now a difference of electric charge across the membrane. This point is called the equilibrium potential for sodium. It's the voltage required to maintain this particular concentration gradient and can be calculated as a function thereof. A typical resting neuron maintains unequal distributions of different ions across the cell membrane. These gradients are used to calculate their equilibrium potentials. The positive and negative signs represent the direction of membrane potential. Because sodium gradient is directed into the cell, its equilibrium potential must be positive to drive sodium out. Potassium has the reverse concentration gradient, hence negative equilibrium potential. Chloride has the same inward concentration direction as sodium, but because it's a negative charge, it requires a negative environment inside the cell to push it out. The resting membrane potential of a neuron is about negative 70 millivolts. Notice that only chloride has the equilibrium potential near this value. This means chloride is in equilibrium in resting neurons, while sodium and potassium are not. This is because there is an active transport to keep sodium and potassium out of equilibrium. This is carried out by the sodium-potassium pump, which constantly brings potassium in and pumps sodium out of the cell. The resulting resting potential, while costly to maintain, is essential to generation of action potentials when the cell is stimulated.
Okay, so the outcome of this session is, okay, you now you understood what is potential, what is biopotential, what is action potential, okay, what is resting potential, then how it is works, then what is sodium pump, etc. Okay, so thank you so much. Study well. Okay, bye.